This is our fifth lecture of the series on modern physics, and today we are going to talk about the fundamental theorems of calculus. But before we dive deep into what these theorems tell us and what is their physical importance, let us recap what we did in our last lecture. Quickly, we'll recap what we did in our last lecture, because that will beautifully connect to what we are going to talk about today. In our last lecture, we talked about three very important operations. We talked about that how we find the change in the scalar field and how we find whether a vector field is spreading or shrinking, or whether a vector field is curving around, or it's looping around, right? So we said that I can represent a scalar field by a scalar function, which is a function of the position coordinates, and then I want to operate it with the del operator, which is a three-dimensional differential operator. It tells me how the phi will change. So since we are dealing in three dimensions, so we will have a three-dimensional differential operator, and we call it as a del operator. It is nothing but your differentiation, or you are finding the change in the function in three dimensions. So that fellow del, defined by a triangle would mean like there are three sides, so it has that meaning of that it represents something three-dimensional. So that is given by this when you hit del operator to phi, we call it grad or gradient function, or it's gradient of, this is how you mathematically tell that it's a gradient of phi. So what does it tell me? It tells me how the scalar field changes, but itself it's a vector, because this del is a vector. So this is a vector quantity, it's a vector field. Could be a vector field, right? It's a vector field. And it has a direction and magnitude. Its direction tells me that what is the direction of the maximum change in the field. So the gradient is always the direction of the maximum change in the field, right? So it's a very important concept in physics, and it's used almost everywhere in electrodynamics, in hydrodynamics. These are the main topics where we use it. Almost I've seen these kinds of interesting things everywhere in physics. Okay. So now what is gradient? Gradient you take on a scalar field, and it gives me how the scalar field changes. And not only in all the three dimensions, as I go around, I have a gradient. As I move along all the three directions, how the field changes is given by the gradient, and then the direction of that change is the direction of this gradient, which gives me the change in the scalar field, is the direction in which the field changes maximally. That is what you learn by taking gradient of a scalar field. Then we have a vector field A, which is used to represent a vector quantity in some region of space, like we have electric field around a charge. At every point you can associate the direction of the field and magnitude. So, or a magnetic field, by that way, you take a magnetic compass and a magnet, and at every point you can define magnetic field, the magnitude of the magnetic field and its direction. So you need a field, a representation, a function which depends on, which is a vector quantity, and which would depend on the space coordinates, and that mathematically I represent by A. So my A is nothing but it depicts that magnetic field, or any vector field. It could be magnetic field, electric field, velocity field, or anything. Right, now I want to know what information I get once I differentiate this vector field. So there are two ways of differentiating it. One, you can differentiate it via a dot product, because your del differential operator is a vector. So I can see how it changes by hitting del operator via dot product. But then what it gives is what it maps to, what it really means. It means that whether your field is spreading out or shrinking. So whether it is spreading or shrinking, whether it is spreading or shrinking. So if the field is spreading out, then it has a positive divergence. If the field is shrinking, then it has a negative divergence. So the divergence tells me what is the field doing locally and at a point, whether it is going, whether it is spreading out, like the electric field due to a point charge, it spreads out, and electric field due to a negative charge, it shrinks in. So that is the ideas that we learn in high school. And therefore, the positive divergence and the negative divergence will correspond whether there is a source or there is a sink. And then we can also take the cross product of with del. I operate del by a cross product to electric field to a vector field. Then this tells me whether it is this field, vector field, whether it is rotating, it is swirling, it is curling or not, whether it is moving in such that it circulates or not. So it's all about, it gives circulation kind of thing, whether there is circulation or not. If there is circulation, then the curl is finite. If there is no circulation, then it is zero. For example, electric field, it spreads out, but it doesn't circulate. So therefore, the curl of the electric field would be zero due to a point charge or due to a charge source. But if you take a magnetic field, what you see, say you have a conductor and you pass current through it, magnetic field curls around, it's going around, it circulates. So naturally, the curl will not be zero in this case, because the magnetic field is curving around the loop, it is looping around the loop, so around the conductor, so it will have a positive curl, right? So curl will tell you whether the field is circulating or not. So it's kind of finding out the circulation of the field. Divergence will tell me that field is spreading or shrinking, and the gradient will tell me there is a scalar field. The gradient is meaningful only to a scalar field. It tells me the direction of the maximum change in the scalar field. That is the direction of the gradient, because it's a vector. So basically it gives the change in the scalar field, and its direction is the direction of maximum change. So now I think we very much understand these mathematical operations and their physical meaning. That's very good. Now we will talk about that. This is what we actually did in the last lecture. Now we'll talk about the fundamental theorems of calculus that relates to these gradients, divergence, and curls. So what are these fundamental theorems all about? Actually, these theorems, what they do is that they connect some local phenomena to some global phenomena. So I will talk about what it means to connecting local changes to the global changes. Right. So let us see the first theorem. This theorem is called the theorem of gradients, right? So what it tells me, that suppose I have a scalar field which is a function of x, y, z, fine. So it is defined in some region, fine. Say a temperature field, say a temperature in a room, tell x, y, z, right? Fine. Now I find the gradient, fine. So what you do is that take del operator, hit it to phi. So this will give you gradient. I can calculate this gradient, fine. Now what I do is that I take a path, say there is a point A here, and there is a point A here, and there is a point B here. So I want to integrate this gradient along this path. So I will calculate gradient of the field from here to here, and then multiply with dl vector. I will take what is the projection of gradient in that direction, and keep on calculating this dot product and keep on summing it, right? So how would I write it mathematically? I will write integral, and I will take this path integral. I will take it over this path which I have chosen path, and then I take del phi, and then take a dot product with dl, and I want to see what that is equal to. So in mathematical language, what should I say? I say that path integral of gradient from one point A to point B, what is that equal to, right? It turns out that this path integral is equal to just the value of phi at B, at location B, which will be some x2, y2, and z2, minus the value of phi at location A. So integrating this field over this whole path, right? Integrating this field, this gradient of this field over the whole path, integrating gradient of the field over the whole path is equal to difference of the field between two ends. So now what I am doing here, I am finding the change of the field from here to here, from here to here, from here to here, and just integrating with the path. And then as I sum it all, it is simply equal to the difference of the field between the two ends. So that is beautiful. A nasty integral, this could be a very difficult integral, is just the value of the function at B minus the value of the function at A. Always keep in mind, whatever is in your integrand should be scalar. This should always be a scalar. Why? Because we're summing. So you sum scalars, because if you make a vector sum, then you need to take care of direction to every point. Every point there will be some angle. You need to take care of that angle, because for vector addition is a complicated thing. And you not only have to add two vectors, but you need to take care of what the angle is, because that sum would depend on that angle. You know how to add two vectors and how to find the magnitude of their addition. It's a complicated thing, root of a square plus b square plus 2ab cos theta kind of a thing. So since integrand is always a scalar sum, so the only way it makes meaningful is that you have a dot product here, because dl is a vector and this fellow is a vector. If this is very important note in mathematical sense, right? So now let me revise what I'm saying, and let me re-say what I said. So how would you put it in mathematically? You will say that path integral of gradient of a scalar function. What is this? This is an integral. Which integral? Path integral of gradient of a scalar function, right, is equal to the difference of the function at the endpoints of the path. I mean, you take the initial point of the path and the end point of the path. You calculate the difference, but that difference is equal to this complicated end. This is your theorem of gradient. The next idea, which is called the next, we go to what's called as divergence theorem, right? Or it's also called a Gauss theorem. What does divergence theorem tell us? So divergence theorem tells us, suppose I have a vector field A, which is a function of x, y, z. Now I can take the divergence of this field, right? So it tells me whether the field is spreading or it's not spreading. So this is a region where you have a vector field A, which is x, y, z dependent, and I find divergence. Now you find divergence at every point, and then you integrate that divergence over a volume, over a small volume, right? Now you know divergence is scalar, so you don't need, just have to integrate over the volume. So there is no, like, you don't have to worry. And anyway, it's a scalar, so you are integrating a scalar thing over the volume. Over the volume, you take a small volumes here and find you first find the divergence and take product with that small volume you choose, right? And then integrate over the entire volume. Right, that's how you do. You take the limits of x, y, and z and integrate over the entire volume, and that happens to be equal to what? Just the flux of this field over the surface. Right, this volume, the interior will be enclosed by a surface, so you just take the surface integral of that field, and that surface integral, which is the flux, that would be equal to the volume integral of the divergence. So that is the power of this theorem, and that it relates volume integral with surface integral. So if my volume integral is a bit difficult to calculate, I can calculate surface integral, and that connotes the same meaning that the volume integral of the divergence has, right? So what it actually does is that I have to see that, you know, what is happening at the boundary. At the boundary, I'm calculating the flux, right? I'm calculating the total flux through the boundary, and that is equal to what is happening inside, whether the field is converging or diverging. That would decide what the flux would be, and it should be like that. If there are sources inside, the field is diverging out, and naturally that would give rise to the positive flux, right? So this connects the divergence of the field to the flux through the surface, and this is how a local thing, which is divergence at a point, that you connect to something global, which is this boundary, the boundary that encloses the whole volume. The flux through that boundary is connected to the divergence inside the boundary. So inside boundary, field is having some interesting feature that is spreading or it's not spreading. That decides what the flux is through the surface. So this theorem connects the divergence of a field to the boundary, from volume idea to the boundary value problem, like, you know, what is the flux through the boundary, right? Now if you want to say it mathematically, how would you say it? How would you say it mathematically? What you will say the volume integral of divergence of an vector field, volume integral of divergence of a vector field over the volume, over that closed volume, is equal to the surface integral that binds that volume, that's around that volume, right? That the surface integral that closes that volume of what? Of a surface integral of a. Surface integral of a. Why the dot product should be there? Because a is a vector, ds surface element is a vector, but the integrand has to be a scalar, so it has to be a dot s. So never get confused about where the dot is, where the dot is not, right? Because I have seen many students always confused whether they should put a dot or not, but now the confusion should not be there. Remember, integrand has to be a scalar, and this comes in almost all important problems that we do in electrostatics. This equation rules, right? Because it contains the idea of the Gauss law, right? The first Maxwell equation is derived through this beautiful mathematical theorem only. We'll get into that. And this also works for electromagnetostatics, and then it can be used in hydrodynamics. There are other fields where the flow, motion of something is important. These equations, these theorems play a fundamental role in our deeper understanding of those fields. Very nice. So we have seen the theorem of gradients, and now this was the theorem of divergence. So gradient theorem, what does it do? What does it give us? It tells us that if you take gradient of a scalar field and you integrate over a path, it's equal to just the difference of the scalar function at 2 points, at 2 ends of that path. And here what it tells us that if I take divergence of a vector field and I integrate over a volume, that's equal to how much field is going out from the closed surface enclosing that volume. So it's connected, divergence of the field is connected to the flux of the field. That is what the idea is here, right? So let's now go to the third important theorem of calculus, which is also called the Stokes theorem. Remember, sometimes people will ask you, what is Stokes theorem? So it's actually the theorem of curls. What does it say? Now, suppose I have a vector field A, X, Y, and Z. Now I want to see it is circulating or not circulating. For that, what you do is to take curl. So you take the curl of the vector field, it gives the circulation of the vector field. So this is the region, and the vector field is locally having curl. So it means every point there is some rotational component, like you have a whirlpool. At every point something is going around, right? So there are these rotational components of the field. Then what you do is that you calculate the curl and multiply with the small surface element ds, right? So I will integrate it and then integrate it. So what I do is that I take del cross A, take curl of the field, and then take its then integrate it. For integration, I need a scalar at the end of the day, so I take dot product with the surface. Right, so I integrate it over the surface. I take a first integrated, I take a product with small surface, then sum all the contributions. So since it is surface integral, right, so that is my surface integral. So what it says, the curl of surface integral. So it says that surface integral of curl over the closed surface, that is the surface, right, that is equal to, according to this theorem, right, that simply is that loop integral of this field over the loop that closes this surface. Now, it's this boundary loop, this loop. So you just take A, take its dot product with L, dl along the bound, along this loop, which this loop, what does it enclose? It enclose the whole surface. So whatever is the surface, it will have the perimeter. So you just go along this perimeter and integrate directly the field, right? That value which you get will be equal to the curl over the surface integral of the curl of the same field. So it connects that the circulation, local circulation, is equal to the global loop integral, right? So global circulation is the result of local circulation. So it tells me what is happening at the boundary is nothing but the sum of the circulations inside that boundary. Inside there are circulations everywhere. So add those circulations, and what does it give me? It gives me the loop integral along the boundary. So forget about circulations, just take the loop integral and figure out that loop integral. It will tell me all those circulation components, like all the things that is happening inside the circulating field, vector field. The contribution of those circulation is nothing but the loop integral. right? So also very important when this theorem, when you deal with magnetic fields, and it is through this we find out the Biot-Savart's laws differential version we can obtain by using this important theorem. So these theorems play a very key role in deeper understanding of electromagnetism, right? So I just revise again what I did. I just rewrite all these theorems. So we have three theorems. Come on, let's see what these three theorems are. So the first theorem is the theorem of gradients, and how do we write it? We write that gradient of a scalar function is the then what do? You take the integral over the path, right? That is an open path, not a closed path. That's equal to the value of phi at one location and locations, difference of the values of the field at two locations. Now, whatever path you choose, this is your A, this is your B. So if you take loop integral here, that would be interesting mathematical idea. I take loop integral of the gradient. What do you think it should be? You are coming back to the original position, so it will be 0. So that means loop integral of gradient over a loop integral of gradient is 0. If you take the gradient and take it over a integrate over a closed loop, you should get 0. Very important result. Remember that. So this is my first theorem. What's my second theorem? The second theorem tells me the volume integral of divergence of a vector field, right, over the volume V is equal to the surface integral that encloses that volume. So it's a closed surface. It encloses that volume that's equal to the flux of the field through that surface. So it connects divergence with the flux. Remember, second theorem connects divergence with the flux. Keep it in mind, divergence with the flux, because I will be using this result. And the third one is that I take the curl of the vector field and I integrate over small surfaces, right? I first take product with small surfaces and then integrate it out over the entire surface. That's equal to the loop integral closed. This is the loop integral. Loop. You have the loop that closes that surface, the loop that closes the entire surface, and that is simply the loop integral of the same electric field, vector field. So loop integral of vector field is equal to the surface integral of the curl of that field. The loop integral of the vector field is equal to the surface integral of the curl of that field. So remember, curl with loop integral, and divergence with flux, right? And gradient with difference of the function at 2 points. This is the takeaway from this discussion. Now let's also discuss the second derivatives. This is also very important before we finish the lecture. This is very important to cover. So now, why is second derivative important? Because in equations of state, in equations these which define the physics, normally we have second derivatives most of the times. In these second order differential equations, they define the entire physics of what is happening. Like you can find the change in the flux or change in the field by a first order derivative, how it changes from point to point. But is that change evolving? How does that change? Because that gives us how curved the field is, how field evolves, how field changes at every location. So for that, it connects to the fundamental ideas of fundamental physical laws. They are mostly second order differential equations. Like Newton's second law, it's a second order differential equation. Equation of a wave, mechanical wave, what is that? It's a second order differential equation in x and second order differential equation in time. And most of the times in physics, diffusion equation or some other equations, the heat equation, and you always have these double derivatives. I think heat equation is a single derivative equation. Yeah, you just check that. So remember this idea of that why we are interested in second order differential equations, because they occur almost everywhere in physics, right? Remember, the harmonic oscillator equation is a second order differential equation. In fact, the fundamental equation of Newton is a second order differential equation. The equation of the waves is a second order differential equation. So that's why second order differential equations are very important. And they not only tell us, see, the first order differential equation tells me that how the field is changing in the neighborhood. Second order differential equation tells me that how the changing field is evolving. right? How does this change evolves? That's very important. Like, position is changing, that gives you velocity, but is velocity changing? That gives you acceleration. So how is that? Suppose you've taken the divergence of, is that divergence also different at different places? Is that changing? So that will be given only by the second derivative. So if we are interested in second derivative, now let us see what we have in store. So we have gradient, right? Then we have divergence of a vector field, gradient of a scalar field, and then we have curl. These are our first order derivatives. Now to find second order derivative, I have to hit again with the del operator. So here I can hit with del operator. I will write divergence of gradient. And this is del square of phi. And this is called a Laplacian. And it is a very important operator. It occurs many places in physics. So del of, and we can actually calculate, it's just nothing but del square phi. It would be like, in Cartesian coordinate is del 2 phi by del x square plus del 2 phi by del y square plus del 2 phi by del z square. So to make you more comfortable, if phi is x square plus y square plus z square, I ask you to calculate it is Laplacian. It would be first time differentiate, then you differentiate again. First you differentiate, find gradient. You will have 2xi plus 2, you will have 2xi plus 2yj plus 2yzk. But then when you take again this differential operator, so you will have twice 2 plus 2 plus 2, that's what it means, taking 2 times differential, and that is 6. Right, so you can give a function to you, scalar function to you, find it is Laplacian. It means just double differentiate its components. That's it. It's coefficients, right? You do double differentiate its variables. Whatever variables are there, x, y, and z, double differentiate them. You will get the Laplacian. This is called a Laplacian. Very important. Then we have now del dot of A, and this is, so you find divergence, or you find divergence. Now, okay. A bit of a thing we have just missed. So we have found the divergence of the gradient. What next we can do, right? So now we have, this is our vector, and this del operator is our vector. There are two possible operations. One is that I take divergence of phi, and this I call as Laplacian del square phi. That's our Laplacian. Now what I do is that I can take a curl of gradient. And you can easily see by, it's a simple identity in vector algebra, that if there are, you have two vectors in the same direction, then or you have two vectors, two unit vectors, you take their cross product, you will get 0, right? So if I just expand it with the formula, the two row entries would be same in terms of the determinant, so you will get 0 anyway. So other way of thinking is that gradient gives the direction of maximum change, so it's not curving around, right? So the curl of the gradient is 0. It's a very trivial result, right? Not in the sense, not very much used in equations, but it's a result which is very important. Sometimes it is important, it gives us a deeper insight about how the gradient works, right? So good so far. So we have two operations with the gradient. One is that I can take a dot product, otherwise I can take a cross product. Dot product gives me Laplacian, and cross product, that is the curl is always 0. So the divergence of the gradient is Laplacian, and the curl of the gradient is 0, right? So that's clear. Now we get into, we have another thing, which is divergence of a vector field. It's already a scalar. Right, it's a scalar. There's only one way of composing a second derivative, is I take gradient of divergence of A. Gradient of divergence of A. So it's not del square. Keep that in mind. But this does not come in picture when you try to relate it to something physical, right? So this is a possible operation, but it's mostly for electrodynamic purposes. It's mostly unphysical. It is mathematically there, but we hardly use it anywhere, so we'll keep it as a definition only, right? So all you need is to calculate divergence. You will get a scalar function and then find the gradient and see whether that exists or not. That may exist, that may not exist, but it doesn't give anything deeper, right? So then we have the curl, and curl is a vector. So again, I have two possibilities. I can find the divergence of the curl, and I can find the curl of curl. The divergence of curl means it has a circulation. It is a circulation. The field has circulation. So when it is circulating, so it's not spreading, nor it is shrinking. So, or you can easily prove that this through vector algebra. You can see that A dot A cross B is 0. So this is 0, right? The curl does not have divergence, right? So this is how we understand it, that this is some vector identity, right? Kind of a vector identity that if you take divergence of curl, that will be 0. And what about curl of A? Oh, that is very meaningful. That is very important, because this contains two terms and they are extremely important when we define fields, field properties. Like the curl of the fields is extremely important because they give rise to what's called as field equations. This identity is very important because of this identity you develop field equations in electrodynamics. So what is this curl of A? So that's equal to, that anyway is a vector, right? So it is gradient of divergence of A minus del square A. You remember del square is scalar, but A is vector. So it's a vector. This fellow is also vector because this is gradient. So that's why I'm not using any symbols here. I'm not using any symbols here. This is scalar. Gradient makes it vector. So it is gradient of divergence of A minus del square A. Sometimes divergence of A is 0, then simply it is minus del square A. This happens many times in electrodynamics, like we take what is called as Coulomb gauge and then we fix the equation. But anyway, it's a lot of time to go there, but you should remember what this identity is equal to. So the curl of a vector field is equal to, it's equal to gradient of divergence of that field minus Laplacian square, minus Laplacian of that field, minus del square of that field. That's what Laplacian means, del square of that field. Okay. So that is, we have introduced all second derivatives, which would be very useful once I develop the theory of electrodynamics. So this is the end of today's lecture. So in today's lecture, we revised curl, gradient, divergence, and curl, and then we also talked about the three fundamental theorems: the theorem of gradient, the theorem of divergence, and the theorem of curl. And then what did we say? We talked about the second order derivatives, because they will come, once I develop these Maxwell's equations, they will be there. So that time I will be asking you that what is this, what do you think this is, so that those equations beautifully tell us a story about what is physically happening. Now, one thing is important. I have not gone into the derivation of these theorems. Since they are theorems, they are not fundamental axioms of mathematical, this vector calculus. They are theorems. So in principle, they can be derived. We can derive them. That would be useless in the sense that in physics, you are finally using these ideas. It is more important to explore the philosophy and their connection to the real physical problems, rather than getting into the mathematical weaving of how these, it's not a mathematics course, but suppose this would have been a mathematics course on vector calculus, then we would be interested in why gradient theorem, how can we derive it from the axioms of the vector calculus, then we'll derive the theorem of divergence, derive the theorem of gradient. Those questions here are meaningless, because our job is to actually talk about electromagnetism and use these results in our electromagnetic phenomena, right? So I understand that, if you're a good student, you will be more interested. Let us derive all these theorems, right? But if you can do it for your understanding, you are welcome. But in my lecture modules, and I will strongly discourage you the mathematical derivation, because then you will lose that what you are supposed to do. So with that, I close today's lecture. I thank you for your patience, and your love and support is always there, and that keeps me motivated to keep on recording such lectures. Thank you very much. And in case you have any problems, any ideas, that please share on the comment section, and I will also upload the slides for this lecture so that you can connect the ideas. Thank you very much.